Hello dear students, welcome to Nuclear Physics 1 lecture number 7. I am Dr. Parvez Ahmed. In this lecture, we will have discussions on nuclear units and dimensions. We will discuss about nuclear length, nuclear time, nuclear mass, and nuclear energy. So let's proceed towards today's lecture. Um, just like I mentioned, today's topic is unit and dimensions and nuclear physics. So let's proceed towards the first dimension, that is called length. What is length and how is length measured in nuclear physics? In nuclear physics, nuclear length is basically, measures are represented in femtometers, and 1 femtometer is equal to 10 raised to power minus 15 meter, and that is usually called as 1 Fermi. So let me repeat it again. Nuclear length or nuclear radius, or we can also call nuclear size, is often represented in femtometer and nuclear physics. So 1 femtometer is equal to 10 raised to power minus 15 meters. So that is also called 1 Fermi. Fermi is the name of this unit in the honor of Enrico Fermi, as a famous American physicist. Then we have, further for this unit, for the nuclear size. Nuclear size, we remember, it varies from 1 to 7 femtometers. Let me repeat it again, that nuclear size basically we measure in femtometers. So here is the definition for the femtometer, that is 1 femtometer is equal to 10 raised to power minus 15 meters. Here you should also remember that nuclear size, that is the size of the nucleus, it varies from 1 to 7 femtometers. So what it means? It means that the nuclear size is not uniform. So nucleus normally has a variable size that varies from 1 to 7 femtometers. Um, what about the nuclear times? So the time scale of the nuclear phenomena range from 10 raised to power minus 20 seconds to millions of years. It's the time scale for the nuclear phenomena. What's the time scale for the nuclear phenomena? The time scale for the nuclear phenomena should be as short as 10 raised to power minus 20 second, and as large as to millions of years. So this is why we're saying that the time scale of nuclear phenomena ranges from 10 raised to power minus 20 seconds to millions of years. We have nuclear reactions that last for approximately 10 raised to power minus 20 seconds, and the example of that is gamma decay. So gamma decay has a decay times that is approximately equal to 10 raised to power minus 9 to 10 raised to power minus 12 seconds. Similarly, we have alpha and beta decay that lasts for a time period range from seconds to millions of years. We have alpha decay, we have beta decay. So the time scale or the time that has been required for alpha and beta decay, it range from seconds to millions of years. Nuclear mass. So nuclear mass is measured in terms of unified atomic mass unit. Now, what is unified atomic mass unit? That we have already discussed in lecture number first and lecture number second, and that will be quite frequently discussed throughout this course. So how we define atomic unified atomic mass unit, or in short U? So it is defined as 1/12 of an atom of carbon 12. So what is unified atomic mass unit? So unified atomic mass unit is defined as 1/12 of an atom of carbon 12. So that's how we define unified atomic mass unit, that in short we represent by small u. So energetically 1 u, that is unified atomic mass unit is equal to 931.502 mega electron volt. So that is how energetically 1 U is equal to 1 atomic mass unit is equal to 931.502 mega electron volt. That is a nucleon has a mass energy that is approximately equal to thousands mega electron volt. So how we calculate how we deal with the nuclear energy. So nuclear energies are conventionally measured in mega electron volt. That is, I mean, normally the units of the energy is joule, but you know that nucleus is very small, so we have to utilize the smaller unit for the energy, that is called electron volt. But in electron volt we use a bigger units, that is million of electron volt. We call mega electron volt. Mega electron volt basically stand for millions of electron volt. That is, we have to multiply the electron volt. 1 electron volt is equal to 1.602 into 10 raised to power minus 19 joule, and m stand for 10 raised to power 6, that is million. So 1 mega electron volt is basically equal to 10 raised to power 6 into 1.602 into 10 raised to power minus 19 joule. I mean, this is the equivalence of mega electron volts in the term of energy units that we call joule. So gamma and beta decay energies are in the range of 1 mega electron volt. I mean, it's the decay energy for the alpha and beta decay, and its range is up to 1 mega electron volt. But the alpha decay uh, with much more energy than in comparison to the gamma and beta, and that require an energy that is smaller than 10 mega electron volt. So I mean, it's much more than the alpha. There's much more than gamma and beta decay. So gamma and beta decays normally involve energy that is equal to are in the range of 1 mega electron volt. But for alpha decay we need energy that is smaller than anywhere smaller than 10 mega electron volt. So nuclear reactions is normally occur with energy greater than 10 mega electron volt. I mean, you are interested in any nuclear reactions, so this is the limit where the nuclear reactions start. That is, nuclear reactions require energy is greater than 10 mega electrons volt. So that's all we have for this lecture. Hope you learn a lot. Thanks for watching, but stay tuned with the next lecture. That will be lecture number 8. In that particular lecture we will have discussions on why electron cannot reside inside the nucleus. I mean, we will deal with some of the logics that why electron cannot reside inside the nucleus. So stay tuned with the next lecture. Till then, bye bye.